can basically put whatever you think are important into this like a structure, and then these are the entities, are the nodes, right? And then you can also have links among them. These are basically relations or like interactions. You know, some genes interact with each other. Some genes like can influence some pathway, right? Or drugs can treat certain disease, can alleviate certain symptoms, right? So these are the kind of relations or interactions, right? So this is a very basic, very much like the basis of many of my research projects. These are the structures. So people have spent a lot of time to create this kind of so-called knowledge graphs, including people working in the web, the web data, right? People semantic web, if you heard anything about that. So it's basically trying to structure knowledge into this kind of graph structure. And even in healthcare, I know quite some people, clinicians and other data scientists or data analysts, right? Working with health data, they also create their own smaller knowledge graphs about certain disease, about diabetes, right? So these structures give a pretty kind of a pretty neat and explicit description of what are the important interactions and how they interact, right? So it's a very explicit knowledge, right? And it's pretty standardized. But the problem is it's never complete, because you have things missed from this structure. And nowadays, especially compared with large language model, which are trained on so large data, right? So they are basically more knowledgeable compared with your knowledge graph, right? The other problem is your knowledge graph usually cannot be directly applied to real world applications, right? You need some kind of a reasoning algorithm or some embedding algorithm, right, to basically make this knowledge more actionable for real world applications. On the other side, we have large language models, right? I think these are maybe people here have heard more about it, right? So these are pretty capable, right? You ask any question, it's going to give you some kind of answers, right? But the problem is it has hallucination, it lacks a domain knowledge, right? And it doesn't know how to plan for more complicated tasks, right? So the problem is, and also when there are new knowledge, right, you just cannot easily update this model. There's a lot of parameters you don't know which really are guarding some of the knowledge, right? So now you have now we have these two things. And my research now one of the directions, right, is about how we can really make the interaction of these two things more more kind of natural, and basically use them to help each other, right? So actually for the knowledge graph, because it's the main problem is coverage, the comprehensiveness of the knowledge, right? So can we use language models to help them grow, right? Help them put in the more key information, in a more accurate way, right, into the knowledge graph, right? And on the other way, can we use knowledge graph to guide the planning or the reasoning of the language models so they can make more accurate, more grounded predictions, or generate more reasonable answers, right? Explainable answers. So this is the whole picture, and we also have some system, more system level design. I won't be doing much of this today. So it's basically more based on federated learning, but it's more like a federated multi-agent system. So you have language model agents and possibly also human agents. They basically collaborate in a conversational environment. So they converse, they talk with each other to solve problems, right? But our system supports the privacy, the security of this the environment, not only in the environment but also after the conversation is done, right? How can we make sure the things that are first thing is things discussed in that conversation are more private, privacy protected, right? And also after the conversation, things are not going to not going to be there, or not going to stay there, right? They're properly removed. So this is the system, right? And in this system, we also try to build in more kind of factors like human value, how we align them, how we alleviate disparity using this knowledge graph. I'll talk a little bit about that, but this is not the major part of it. The research has been supported by NSF and NIH, and also quite a few industrial partners, basically providing us some credits to run the models, fine tune the models. Right? So this has been very helpful. So again, like one knowledge graph, right? This is just another like picture, pretty abstract, pretty cartoon, like a very simple knowledge graph, right? But we have more complicated ones, right? The idea is, right, again, there are, I think that I should have been introducing the knowledge graphs in this slide, but I talked something about them already. But the more important thing is there are risk factors interacting with each other, right? And they, my research, a very unique part is we want to particularly look at these interactions, how they are going to influence our prediction models, how we can get some insights from this kind of interactions instead of just using single factors or just a combination of factors to explain the things. Right? We want to use try to say, let's say, these two things, this particular symptom and some drugs taken in the past, they interact in a way to influence your outcome. So this kind of things. There are a couple of particular properties of the knowledge graphs. My research really studied in the past, just to provide some context of this this new research direction. Right? One is the heterogeneity of the knowledge graph. So usually for graph learning, people consider social networks, you have users connected, following each other, likes each other's comments, right? So this knowledge graph is heterogeneous. So it has different kinds of entities, right? You have disease, you have genes, you have drugs, right? Other kinds of entities. So technically, there's a lot of things to do because you usually when you look at a homogeneous graph, right, you are just looking at pairs of nodes or certain shapes like a triangle, like a densely connected league, right? These kind of things. But if you consider a heterogeneous graph, there are more complicated patterns. So different entities, let's say a drug and a disease and maybe a gene connected in a certain way, right? They may carry a certain type of pattern, right? Certain type of meaning, right? So this is so this makes the pattern mining more complicated, I did a lot of this research in the past, just to, let's say, automatically find some important patterns on this kind of heterogeneous graph. These are mostly my PhD work. So the other type of graph we studied in the earlier years when I came to Emory is this kind of hierarchical graph. You have diseases and there's usually some kind of ontology underlying these diseases, right? There could be ontology underlying other types of entities too, but disease is just a very a direct example, right? So you have this entities, right? And you so yeah, someone's joy. If you want to ask something, just let me know. So we have this ontology, right? And your ontology basically is giving a known hierarchy of the entities, right? The ICD-9 or the mesh of ontology for the diseases, right? So there are some diseases that are sub-diseases of the other diseases. So why this is important? So the importance is once you know the belongingness, the relation, this kind of relationship between the diseases, right? There are certain symptoms or certain drugs that can be probably can be shared across the diseases, right? But at the same time, you also know there are some specific properties of a sub-disease, right, that needs a certain treatment. Right? So this is kind of so you need this kind of understanding to really make better decisions, make better use of the data. And so this is also kind of a structure we've been working on. I have an example about how we work with this structure in this talk. So basically, technically, you need some kind of embedding space that is more friendly to this kind of hierarchical structure. So you don't need a lot of repeated space to model their properties. So finally, this one is actually the most I'd say it's not necessarily the most hard or important, but it's kind of the thing I'll be talking about more today. So it's called a hypergraph structure. So the idea is in a knowledge graph, right? A general knowledge graph, some diseases interact with certain drugs, certain certain treatments, right? Certain other risk factors, right? But this kind of interaction really needs to happen in the context of certain patients, right? So some kind of interactions happen for one patient, doesn't happen for the other patients, right? So you need some kind of context. So we invented or we basically used this like so-called hypergraph to model the context of interactions. So the thing is that you have this pairwise interactions, but at the same time, you also create this so-called hyper edges, basically to cover certain set of entities. Maybe this hyper edge corresponds to just one patient visit, right? These things are observed like during their visit, or they like just correspond to one patient, his or her whole like medical history, right? How these factors are going to interact, particularly for him or for her. So we basically proposed to use this hypergraph structure to model this kind of context, so the model can really reason or can really leverage like this distinction between people. Right, and I'm doing like a subtyping a lot, so this could also correspond to just a subgroup, a subtype of patient. Right? And we'll see how that is going to really work, like a particular model design and the thing we can get. Right? So yeah, this is a slide I added just for this talk because we want to talk more about like risk prediction, subtyping, and our recent work on joint like phenotyping, genotyping. So this is the architecture. Basically, we have hypergraphs, right? So each of the nodes is a risk factor. It could be like a particular disease code, a medication code, right, or a treatment procedure code. It also could be some like a more continuous value, like people's age, people's blood pressure, things like that, right? But we use different kind of models to generate the different embeddings for the corresponding like embeddings for the type of nodes, right? And that is related to what I did before on the heterogeneous network, right? So basically, because there are different types of nodes, we need different encoders, different model to generate the proper embeddings and align them like for the model for the model for further reasoning, right? And these are the hyper edges. So these basically are modeled as patients, right? In a simple case, when you don't consider many different visits or you don't consider the real like complex progression of the disease, right? You just model each patient as a static node, right? A static age, right? Nowadays, like we are doing like more of a dynamic hypergraph model, which takes multiple visits of the patient into consideration. But this one was like a more static. So then you have this kind of graph, right? Then the idea to do subtyping, our first paper on subtyping was basically on, so that was the subtyping, the KDD paper was basically on like, can we learn a joint clustering or a joint like a grouping of the nodes and the edges on the two sides, right? So what that means, right, on the feature. So remember, these X are basically risk factors or the features of the patients, right? So we want to find subsets of features that lead to subsets of patients, right? So basically, you have a subgroup of patients, and they will share some like common features, right? So this naturally becomes like a co-cluster problem on the two sides, right? So we implemented this co-clustering algorithm on top of the hypergraph model we built before, right? The hypergraph model was in that research paper too. So the basic paper was in EMEA. It's about just using hypergraph model to predict, right? To make predictions on future risk, right? And then we actually added a counterfactual, factual reasoning kind of a mechanism. Basically, the idea is we use a transformer for the hypergraph, but we can use the attention weights to actually already get the sets of important features, right? And then but these features we know like attention like is also sometimes can lead to spurious like explanations, shortcuts that are really not the causal kind of features, right? So like Bo was in that research, so we invented like a more kind of counterfactual, factual reasoning architecture. So the idea is we take out some of the features to make the prediction, and we want these features we take out to really be so-called counterfactual. So we take out this feature, the prediction will change, right? And if we make prediction on this subset, particularly, the prediction will be the same as making the prediction on the whole set, right? So this is a factual and counterfactual, right? So we added that part. We got a counterfactual, factual reasoning like model And that model was basically shown to provide more reasonable explanations on the features of certain patients. Right? Mo and others helped us annotated some of these results. We got 70 or 75% where the counterfactual kind of explanations are more reasonable than the attention-based one. Right? The idea is basically we know this patient has CVD in the end, right? And there are this set of features, that set of features selected by two different algorithms, right? And we asked the Mo and others to help us check which set makes more sense and why some of the particular factors made more sense. Right? And that paper, we got the best paper award in ML4H in 2022. So yeah, that was kind of the original work, right? And then this work, basically, based on that, we added this a co-clustering thing to get the subtyping going, right? And that one nowadays later on that one was only on the clinical risk factors, right? Those procedures, medicine, disease codes. But then collaborating with Dr. Sun here, we got we added in the gene data, the GWAS data. We did select known SNPs known to be related to diabetes. And we added this as nodes into this heterogeneous graph. And we did another kind of analysis, basically try to see a combination of gene factors, genetic factors, and clinical factors. Can we get more explanations? And one of my students now jointly mentored by me and Dr. Sun is really doing deeper analysis over these factors. We are trying to wrap it up for a bigger paper. But the original, very previous, even the very previous preliminary results we got from there, got the best paper award from MedInfo this year. And that was the first place, not even a student paper. They didn't know it was written by a student. So they gave us the regular best paper award just a few weeks ago when I was in Taipei. So this series of work is actually very interesting, and it's of course still the major thing I have to do in my K award, and it's I think it still has two or three more years, so we can still work on that progression part, and we are also working with some people in Florida, in Indiana University, so basically to do more do this kind of analysis for obesity as well. And also do more analysis basically over the progression. So we can do try to find subgroups that really progress to different outcomes. So we can hopefully design better treatments, personalization. So that was more the risk prediction subtyping work, and more kind of a higher level structure, right? Methods, right? Here we besides that, we are one of my pretty heavy kind of work was on the brain network analysis. That was actually the thing got me into Rollins. It got me into the BIOS department, because I was collaborating with a faculty member called Ingo there. We worked a lot on brain connectome. Because my earlier research, a lot of them is on graph neural networks, and we applied a lot of different graph neural networks to design certain tricks to really make them work on this kind of brain graphs. Right? So this is basically another direction, and nowadays we are very interested in studying the some neuroscience kind of discoveries underlying a brain connectome. Right? One of the recent papers we are working on is really, we want to decode the images we see from the fMRI data, right? And but the fMRI data, is very noisy and very very coarse. So it's very hard to decode a very accurate image. But what we found to be interesting was if we decode the semantic concepts first, right? We try to, that is actually pretty easy to decode. So actually your fMRI tells you what you are thinking about, right? When you see that image, right? And then we use a text to image generator, right? Really just conditioned on your fMRI signal, right? we can recover the image pretty well. So this is just one example. Like we are currently doing more on neuroscience, a little bit further away from healthcare, but that is also one of my interests. If you are interested, I know some people work on like still work on imaging stuff. I think that is also a very interesting thing to work together. Yeah, and we are also applying this kind of imaging analytical tools, the multi-agents for like imaging processing. We are applying that to aging-related diseases, stroke-related disease. I'm collaborating with the School of Nursing on that, and that is also like multimodality kind of way. It's a pretty popular thing to do, right? These days. The other direction is the thing I am going to talk about more today. So like we have heterogeneous clinical data. We started from like the EHR and the clinical nodes, right? That's already heterogeneous because you have like different types of nodes. You have different types of structured EHR, right? And then you have different types of nodes, like your like admission nodes, like your discharge nodes, your like nursing nodes, right? Different kinds of nodes, right? This is already pretty heterogeneous. And then we also work mainly working with Dr. Sun and some others on like omics and other kinds of omics. And nowadays there's some new collaborations being formed about transcriptomics. And I think that's also going to be like hopefully with more patients that do have both the clinical data and the transcriptomics, so we can get a better like large scale analysis on that as well. But everything we started with EHR, and we are just combining this with EHR. Risk prediction. So these are the tasks I work on, right? Risk prediction, subtyping, treatment, and progression. This we've been making like small steps, like all the time. So here is the thing, right? The kind of the real like technique about how we can really use language models or like large models, large foundation models, multimodality foundation models, all this like fancy recent stuff, right? Make use of them to really help us create better knowledge graph, right? And sometimes because this proposal. This whole thing, this was more like created later last year. Nowadays we have a few months like already passed, and this already actually is updated as well. So now we are actually not looking at only the traditional knowledge graphs. We are looking at the knowledge base, and that knowledge base is basically a so-called agent-facing knowledge base. Agent means like your large language model agent or your human agent, right? But these agents, they are using the knowledge graph to basically reason about the problems, reason about your medical questions, reason about the mechanism of a disease, right? Whatever. So they are basically relying on your knowledge to do that kind of reason. So this knowledge doesn't have to be in a graph structure, right? It could be just a few very crisp like sentences, right? Describing the key factors you need to consider for this particular disease, right? Or it could be like some key knowledge about like your medical guidelines, right? Like if you get this disease, you go to hospital, what kind of procedures you will likely go through, right? This could be this kind of knowledge too. And it could also be something you extracted from your patient data, right? Let's say one patient come, right? You just have a EHR retrieval. We have this EHR agent we built last year, right? It's basically about if I ask a question about a certain disease and I ask a question about a certain kind of basically a certain patient, right? He or she has this ABC, this like a diseases diagnosis right, in the past, right? And now she has like this ABC, like blood pressure, this like glucose level, right? What we should do for her, right? Or for him, right? So this EHR agent basically is when you get a certain like amount of patient data, we will use language model to write like a Python code to basically retrieve similar patients from your database, right? And now like we call this experience RAG, like experience-based retrieval augmented like generation, right? So you get similar patients, and then you try to like work on your treatment plan based on these similar patients, right? How their outcome, what kind of treatments they get, and what kind of outcomes they get, right? So using this kind of data to really reason or plan about your like treatment plan for this particular new patient, right? This is the EHR agent, right? And so basically that basically says there are different types of knowledge, right? Some knowledge could be in the existing knowledge graphs already. Some could be like in your literature, some newly published literature about new clinical trials or new drugs, right? And this could be like, and then on this side, it could be like, this knowledge could also come from your database, right? Your hospital database, your local hospital database. Like this could be really multimodality, EHR, your omics, like your physiological waveforms, medical imaging, your service you need, right? Even some of your out of the hospital data. Right? So this part is really like the more kind of the future, right? In my kind of understanding. So anyway, there are three types of work under this trust. Like when I wrote the proposal, so this in the beginning it's all about you get knowledge from different sources, right? How can you put them together in the first place? Right? The different people created this knowledge graphs using different terminology, right? Different coding systems, right? Even this data cleaning, I talked with Xiangqin in the past. She spent her whole career working on cleaning EHR data. So when we have different data, how can we put them together, right? This actually is made very, very much easier by the large language models. Right? We'll see one of the examples one of the first works we did to use large language model to do this kind of alignment between knowledge graphs. And on the left side, where people have been doing this all the time, extracting new entities, finding new concepts, finding new relations, basically new triplets, right? From literature, from text data, right? And we did that before there were large language models, right? We use NLP tools, right, to create this so-called concept maps from literature, from documents, right? That was published I think one paper was doing my own PhD, and another was one of my PhD students took up the work to build a more complicated graph generation model. But nowadays we are also using language models to do that. So the idea is you can actually take a subgraph out from your knowledge graph, right, and then retrieve some documents that you think is describing this subgraph. And then you basically can create new subgraphs using your large language model, using just prompt design. Tell the large language model what types of entities you are looking for, what type of relations you are looking for among certain types of entities, right? And then ask the language model to create a small subgraph for you. And you can compare this graph with your existing subgraph, right? And then you can see which part needs to be updated. And of course, this is very hard to do, especially for evaluation, because you don't have ground truth for that. So nowadays, my students are working on automatically evaluating that using multi-agents, using language model agents, right? That is also a pretty interesting work. There is a new conference my friends in Stanford just created. It's about using language model agents to do research. So in a lot of conferences or venues we are working on nowadays, right, we want to avoid people using AI to write papers to do research, right? But that particular conference requires people to do that. So we are basically acting as advisors. We are acting as humans to advise the language model, to teach them how to do the research, right? And also teach them how to write a paper. So there is a paper my student is working on, basically to submit to that conference. So we are using a multi-agent system to evaluate a particular language model task. Right? It's pretty interesting. So that is on the left side, and on the right side, right, we are having a lot of work ongoing here. So, but the key idea is we want to use language as a bridge to really combine different modalities, right? Like the example we showed, in neuroscience, right? Actually, we already find it's actually people's brain is more wired to reason with text, to reason with language. That's probably why language model is the only successful foundation model so far, right, for different types of data, modalities of data. So this we are kind of leveraging this finding. Basically, when we create knowledge graphs, these knowledge graphs are text-based. Right? We're adding different modalities, entities with different modalities, but these entities will still have a textual description and paired with a domain modality specific embedding. Right? let's say for physiological waveforms nowadays, we build quite a few like so-called physiological waveform foundation model, ECG foundation model, right, with the School of Nursing. And this foundation model, hopefully, ideally, it understands all different kinds of physiological waveforms, right? And even some interactions among them, right? Your blood pressure maybe have some like interactions with your ECG, right? So this is this kind of research. And but what we are going to do with that is we'll use this foundation model to encode any like a patient's neurophysiological waveform data, right? And just get an embedding for that. And then we are also generating like a description for that, because the physiological waveform foundation model can understand some of the physiological waveforms, right? And it's also trained on pairs of like a physiological wave data and the report data, right? So hopefully that model can generate a piece of text already, right? So then we can put that piece of text together with that embedding into our knowledge graph, right? And in this way, we can try to align this like embedding space of this modality of data and our text data, right? And then hopefully the language model then can do reasoning like between them. And so this is like an example, but also there are a couple of works basically just trying to see how we get a better like a multimodality foundation model that can help us extract this kind of multimodality risk factors, biomarkers from patient data, right? One of the work we published last year is MedVital. It's basically done by my like a student who graduated already. And she basically we took out like we were looking at medical imaging and the medical reports, right? Like the imaging reports. But the problem is you want to find this kind of regions in your medical imaging, right? Really like inside this region, you can see some kind of a lesion or some kind of a blood or something, right? But when you see that corresponding report, right, it usually don't tell you exactly where the physician finds the problem, right? So you don't have that kind of fine-grained data for you to do like training, for you to really train a model to understand the particular imaging, the particular problematic regions in the imaging, right? So what we did was we asked that work we were collaborating with folks in Harvard, in MGH. So we asked the doctors to provide us with some like examples, like 50 or something, I think less than 50, less than 100 for sure, examples of this fine-grained like annotated imaging and the corresponding text, right? And then we use GPT-4 vision at that time to basically follow these examples to generate more this kind of annotated imaging, right? But of course, they did a pretty cool job, but there are still a lot of like wrongly generated images and text, right? And then we asked this clinical collaborators to further annotate some of the generated imaging by GPT-4V, right? And then we used this annotated data to train another model to basically that model is going to determine whether a generated data pair is good or not. Right? So that is kind of a framework. Then once you have this model and you combine it with your GPT-4V, then you can basically generate unlimited amount of data and use that model to classify which is good or not, right? So this is basically the idea. So how you can really very efficiently put your physician or clinicians help. So you can magnify that help and replicate it for a larger data scale, right? So that is just another work we just did for that hopefully can help us improve the foundation model of particular modalities. So here is here is a work we did actually 2 years ago. So that was the very first work we did to use large animal model to align knowledge graphs from different sources. I'll go very briefly about it. It's technically is also very pretty straightforward. Idea is you get knowledge graph from different institutions. And the problem is you have so usually we start from an existing ontology or hierarchical structure, right? Here is a hierarchical structure from ICD-9, I think, about diseases and their subdiseases. And then there is a new knowledge graph, and there are some like diseases you just don't see directly on your like existing ontology, right? Because they use different terminology or whatever. So the idea is you want to find the closest entity, right? So each of these new entities in the knowledge graph is called a query entity, and now you want to find a closest entity in your existing ontology that is basically hopefully the same to your like query entity, right? So that is a pretty like a neat problem, right? Of course, there are a lot of like nowadays there are a lot of new works we are doing to improve that, right? To create a better like an agent that can double check your like your alignments, right? Or to basically, if this doesn't align, right, what should we do? Should we add a new node somewhere to include it, right? So that is some of the ongoing or the more recent works. But this work was pretty like straightforward. So basically, we got a query entity, and we are going to find we are going to use a retriever method to basically find the like candidates for it from the ontology, right? Because you basically you can put the whole ontology into a large language model conversation, right? To ask which is the closest one, right? So we first use like a retrieval method to find like a subset of like candidates, right? And then we put the candidates with that query entity into the language model to ask it to re-rank these candidates, right? Which one you think really is the most like closest, right? So it's pretty straightforward method, right? But we just created some tricks, right? The first trick was for the retriever. The idea is you want to get all of the potential like candidates, right? You don't want to exclude some like candidates, then you are never going to find them back in the re-ranking, right? So what we did was because these entities came from a knowledge graph, right? So we can take their properties, we can take their neighbors on the knowledge graph, and we can add them into the retriever. Right? So you can retrieve more like potentially relevant candidates. And then in the re-ranking part, right, what we did was we also tell the language model how the ontology looks like around that entity. So how the ontologies already look like for your query entity, right? So that basically helps the language model to really like understand the problem better. So this was a data sets we created for evaluation because you need some data sets that do have certain different like a certain amount of like entities that are basically the same entity but don't have the same name. Right? So at that time we need to like find data sets that can really allow us to do this kind of evaluation. And we compared with anything we could find to compare with, right? We performed much better, especially in 0 shot and 1 shot when we don't have a lot of training to train an alignment model, right? Your language model basically doesn't need a training, right? You just ask. So like we compared with most of the methods that can do unsupervised learning, like some embedding methods, or some methods just compare by comparing the words, right? So you can imagine they definitely perform much worse. And we checked our tricks, and we checked like with different language models, right? At that time, GPT-3 was the most powerful one, and it does give the best performance. And all of the models actually get improvements. The point is that if you have a smaller model, right, your improvements is actually bigger, right? Without content and with content, right? You basically you can check this like improvements is better for the smaller models, and that is a good thing because in hospitals, right, we don't use large models at all, right? Or mostly we don't use this like black box, commercial, expensive, and maybe they are stealing your data. This kind of models. So these are some case studies. We also got like help from from our collaborators, and this was an example I find myself without much medical knowledge. I find it's pretty intuitive. So you have a query entity called some short stature obesity syndrome, right? And if you ask your model to find the closest one, right? Sometimes you find this short syndrome, right? Just looks close, right? Seems like pretty close. But something is also about, let's see, sometimes it actually find this one, but this one is incorrect because this thing is some kind of disease of anatomical entity. right? But this syndrome, this obesity syndrome, is not this kind of an anatomical entity disease, right? So you basically, this one is actually wrong, right? So you should put it here. So that basically says if your language model has a better understanding of this ontology, it basically, if we give this ontology to it, right, then it will make the right prediction. Otherwise, this is just like one of the examples. So one of the examples of why you're like letting your language model know some structure of the data could actually help. So yeah, I should be really quick. So this is about how you can use your knowledge graph to reason, to help your language model do reasoning. I will just briefly go through this. So we have like so there are a lot of work on this like recently, right? So I kind of categorize them into three types, right? One is you check your you use a knowledge graph as a retrieval, a source of retrieval, right? So you can check knowledge, right? You basically use the language model to check whether use your knowledge graph to check whether this feature is helpful or not, right? So this is basically the one of the preliminary experiments we did, right? So we fine tune, we do inconsistent learning for the GPT-4, but it barely outperforms the more traditional machine learning models, right? Because they make a lot of basically false positive predictions. And that false positive is because you give the language model a lot of features, right? And then it will try very hard to just make connections between each of the feature and your outcome, your outcome label, right? And then it will think everyone should have that. Everyone will get that disease. Try to be very cautious. So what we did was one of the examples was this EMEA paper this year. So basically, we find that the really relevant entities inside the knowledge graph first, right? And we get rid of the less relevant ones, and we only give this more relevant ones to the large language model to do the reasoning. Right, so now it basically reduces a lot of false positive, but it still gets a relatively good false negative. Right, so that boosted the performance a lot. So there are a couple of works kind of a similar kind of approach. Basically, you first retrieve something from the knowledge graph as a guidance for your language model. Okay, the other one is more complicated, more computationally heavy. So the idea is you use your knowledge graph to help you generate more training data for your language model to do a fine tuning. One example is nowadays what we are doing is you have more like a medical question or more like still let's say an outcome prediction, and you have some features, you have some input features, right? And the thing we did first is find a reasoning path, basically find paths between each feature and your outcome on your knowledge graph, right? First, find this kind of path, and then use a very strong large language model like GPT-4 or 5, right, to generate chain of thoughts based on these paths, right? And then you use this generated chain of thoughts to fine tune a local large language, right? So that way, you teach the language model to reason based on your reasoning paths, actual paths on your knowledge graph. But that in the same time, you are teaching it how to reason based on the better large language model, reasoning, logic. Right? So that is one of the work we do. So this a series of work we did on that. And finally, the type of work is on reflection. So after you generate a question, generate an answer, or you generate a prediction, right? Can you look back at the knowledge graph, right? Can you basically decompose your answer or reasoning into steps, right? And then you check each of the steps on your knowledge graph, right? If of course, when you decompose, you need a large language model. So you tell the large language model how you want to decompose it, right? What kind of relations, what kind of entities you want to decompose your answer into, right? And then you check this on your knowledge graph. So in that recent a PJ paper, we basically showed that if we use knowledge graph to help us build a reflection to basically validate the performance of different models, right? That validation actually correlates to humans validation. Right? So your knowledge graph actually is going to do kind of similar job as your human in terms of revalidating your your large language models predictions. Okay. So I won't be able to go through the details of this work, but the idea is we again on our hypergraph model, we basically added a knowledge graph based retrieval process. Right? So the idea was that you have a hypergraph, right? Each node was a risk factor, but this risk factor, our hypergraph model only models the interactions among the risk factors, but didn't really leverage the semantics of these risk factors, like what each factor is about, right? What each factor is, right? If we use a knowledge graph, we basically generate a summary of each risk factor using things we retrieved from a knowledge graph, right? And then we co-embed that summary and this hypergraph structure together, right? Using two models, a hypergraph model and just a text language-based model, right? And we do a joint prediction. We're doing like a co-training on these two and make a joint prediction. So that was able to improve the performance, and also we did some annotations with our collaborators as well, just to show that language model, that knowledge graph retrieval based summary for each risk factor is actually better than you directly ask language model to generate a summary for you. But we can also use knowledge graph to evaluate the language models at scale. And this is a federative learning system. I don't want to go much deeper into it. It's just it has some major components to basically make sure your conversation is private, and each of your agents, no matter it's a large language model agent or a human agent, is really not talking about things they should not be talking about. And then the idea is eventually after the conversation, we make sure nothing really is left, right? Nothing really. So during the conversation, no parameters of the models are updated, right? After the conversation, how can we safely how can we double check the language model didn't really learn anything from the conversation, right? So this is the kind of more like a federated multi-agent system. And we want to be able to engage humans, and we collaborate with I think it's UT Health and UT Austin, basically to they constantly recruit stakeholders of from different places, and basically ask them to help evaluate the language models we build, basically by looking at the answers and then score the answers in different perspectives, and giving feedbacks on how this might be improved. Right? So this kind of information can be always used to fine tune the language model, and also this SDOH based knowledge graph. We are building a knowledge graph basically based on SDOH. So hopefully more of this, if we have more of this kind of entities and their relations inside our knowledge graph, then we can do we can use this new knowledge graph to support more SDOH aware reasoning. Okay, so with that, I would like to thank my advisor. Thank my advisees and my collaborators, and yeah, thank you again for having me here. Yeah, questions are welcome. Yeah.
Thanks, Carl. Always, I'm learning a lot from every time you present. A lot of exciting words. So one question I have is really about when you, I understand on the research side, right? So you always try to incorporate a different options, for example, the large language models, but they're evolving, right? So, for research, you can always compare and to demonstrate improvement, the performance, but for the applications, I wondered, based on your own experience, what would be the point we can make a decision, either they're good enough or we still need to constantly update it? Because on the clinical side, people, they don't want to change or the uncertainties, right? They prefer something fixed, like a guideline, they know exactly what to follow. So between the two kind of sides, right, research and all these kind of really exciting kind of improvement, but on the other hand, how we're going to use them.
Right. So very good question. So we did a lot on evaluating the language model based agents, right? So I would say that at least 1/3 of our work is on how we can choose the best language model agents. Right? For example, that work I was talking about that we're submitting to that agent conference, right? It's basically about how we can create an agent-based framework to choose the best, we're doing PHI annotation from nodes, right? To choose the best annotating model, right? So that is one thing I think we can always do. We can build more like evaluation methods. But I think that still doesn't answer your question fully because even your evaluating agents are progressing all the time. So you can still now you do this evaluation tomorrow you can do a better evaluation. So this model still needs to update. I think that is very hard. So another thing we can do about that is at least we are working on some more like a generic kind of agents, right? So these agents you can, so for example, I want to have an agent to be able to do diabetes diagnosis, right? And I'm using like a knowledge graph, diabetes like a specific knowledge graph to support that agent, right? So hopefully, if we use a certain language model to be that agent, and then we add another like tomorrow we're putting a new language model, right? That switch won't be very hard. It could be pretty easy, right? And our knowledge graph is also a pretty easily editable thing. So if you want to add new things, you want to replace it with a better graph, right? It's also hopefully the switching itself won't be very painful. So that I think helps a little bit too. But still, I think there's no end of creating new things, and we just need to keep updating.
Do you think it's possible to, for the field to set up certain kind of standard? I mean, it's kind of semi-automated, but we can somehow build the evaluation system so whatever the new versions coming out, it will be only better, not worse, right? Or some kind of evaluation and also somehow managed with human beings. So that way, there will be some kind of consensus both on the computational side and human side. So there will be. Right. Well, we're not sort of waiting on the best technology, but also we are not introducing uncertainties GPT-5 comes out, but people they like version 4, right? They have to bring it back, right? That would be kind of chaotic in clinical more than just the online search engine or chat bot, right?
Right, that's a good idea. I think benchmarking is always progressing as well.
So, Carl, I mean, very fascinating talk. You've done covered so much. Can you talk a little bit more about your experience collaborating with a biomedical informatics scientist like Jan? What is it that somebody who is not from computer science background need to communicate with you in order to understand what problems can be appropriately tackled using these kinds of methods?
Yeah, that's a very good idea. That's a very good question. I think I've formed mainly two types of collaborations. One is I think this expertise is really needed in my research agenda, right? When I talked with Mo, at that time I was applying for my KA award. I think I need someone who knows diabetes, right? Who knows what is really important for diabetes, right? So this is I call it the project that I lead, right? So this kind of thing, I think actually. I find it easier to collaborate with people who at least appreciate computing approaches. I think that is good enough. They don't need to understand computer science a lot, but at least they appreciate computing, right? And that's good enough. The other way is more Dr. Sun and more of my recent collaborators who also they have. I think Dr. Sun is both, right? I need some of his expertise for the omics analysis. So I reach out to him, but later on he has his own research agenda as well, and he thinks that some of the older computing tools can be replaced or can be improved by AI, right? And then we got a lot of opportunities to work.
Can you give an example of that, something which was replaced?
Right. So for Dr. Sun's project, I think one of the example was a hypergraph model, right? We can use like traditional models based on like vectors to make predictions, right? Now I have this hypergraph model, then we can actually use this hypergraph model as the backbone model, right? And then further develop techniques, let's say, to incorporate new features, to do like population analysis, to do like a genetic features analysis, right?
Yeah. So one simple example is like we used to do the clustering, right? That's traditional machine learning. And then we do the like old machines, like all these penalized machines and regressions and random forest, right? But now we're seeing the opportunity we can do both together and have even better performance, right? So that's a perfect use case working with Carl and his team.
Absolutely.
Yeah, I was just checking online. I think there's no actual question there. Just people are asking about my stats. Yeah, this stats is on my website too. So I'm happy to share.
Yeah, thanks.
Thank you.
Thank you. Thank you. Thank you.